Welcome back. In today's video, we're diving into the nomenclature of alkynes step by step, in the simplest way possible. Let's dive into the core rules for naming alkynes. Remember, these are hydrocarbons defined by that powerful carbon-to-carbon triple bond. Because of that bond, their names will always wrap up with the suffix -ene. Now, let's look at step 1, finding the longest chain. In basic alkanes, you just look for the longest continuous string of carbons. But for alkynes, there's a major catch. The parent chain, the one that gives the molecule its main name, must include both carbon atoms involved in the triple bond. Think of the triple bond as the guest of honor. You can't have a party without them. Even if you see a longer path of carbons elsewhere in the molecule, if it doesn't include that triple bond, it cannot be your parent chain. For example, imagine you're looking at a molecule where you can count a straight line of 6 carbons, but the triple bond is hanging off to the side on a shorter branch. If that side branch allows you to form a chain of only 5 carbons that includes the triple bond, you must choose that 5-carbon chain as your parent. In this scenario, your molecule is named as a derivative of pentyne, not hexane. The priority always stays with the bond. Alright, you've found your longest carbon chain. Now, we need to give those carbons an address. This is step 2, numbering the chain. Think of the triple bond as the most important guest at a party. We want to give it the smallest house number possible. The rule is simple: always start numbering from the end of the chain that is closest to the triple bond. For example, if your triple bond is between the second and third carbons from the left, but would be between the fourth and fifth from the right, you start from the left. In this case, the triple bond gets the number 2. We call this the locant. We always use the lower of the two numbers that the bond sits between. But what happens if the molecule is perfectly symmetrical? What if the triple bond is exactly in the middle? Here is your pro tip: if the triple bond is at an equal distance from both ends, look at the substituents. Those little side branches are extra groups. In this specific tiebreaker scenario, you start numbering from the end closest to the first branch. So, if the bond is dead center, but there's a methyl group hanging off the second carbon from the right, you start your count from the right. The goal is always the same: keep those numbers as low as possible. Triple bond first, branches second. Once you've got your numbers locked in, you're ready to name it. Now that we've identified our chain and numbered it correctly, it's time for the final act. Step 3. Assemble the name. The template we follow is substituent location, hyphen, substituent name, then your parent prefix, followed by another hyphen, the bond location, hyphen, and finally, the suffix -ene. Let's look at our example, 4-methylpent2-ene. Let's take it apart piece by piece so you can see how it was built. First, the 4-methyl. This tells us there is a 1-carbon branch, a methyl group located on the 4th carbon of our chain. Notice the hyphen separating the number from the name. Next, we have pent. This is our parent prefix. It tells us the main chain is exactly 5 carbons long. Then, look at the -2-ene. This is the most critical part for an alkyne. That 2 tells the reader exactly where the triple bond starts. Since it's a 2, we know the triple bond sits between carbon 2 and carbon 3. Finally, we end with -ene, the signature suffix that screams, this molecule has a triple bond. When you put it all together, 4-methylpent2-ene, you've created a unique, scientific, social security number for that molecule. No matter where you are in the world, any chemist looking at that name will draw the exact same structure. And there you have it, you've just mastered the art of naming alkynes. So, you've mastered the single triple bond. But what happens when a molecule levels up? What if there are 2 or even 3 triple bonds in the same chain? Don't worry, the rules don't change. We just use multipliers to show the world exactly how many bonds we're dealing with. The multiplier rule: when you have 2 triple bonds, the suffix -ene becomes -adene. If you have 3, it becomes -atrine. It's like adding a prefix to the suffix. Take a look at the structures on your screen. On the left, we see a chain with 2 triple bonds. Notice the numbering starts from the end to give those bonds the lowest addresses possible. Since there are 2, we label it as an -adene. On the right, we have a more complex structure with 3 triple bonds. Following our rule, this becomes an -atrine. The hidden rule. The extra A. Now, pay close attention to this small but vital detail. When we use these multipliers, we have to keep the letter A at the end of the parent prefix. For example, a 4-carbon chain isn't just, but, it becomes, Buddha. So, a molecule with triple bonds at positions 1 and 3 would be named Buddha 1, 3-dene. Without that, A. The name sounds clunky, it's the glue that holds the name together. Just remember, count your bonds, pick your multiplier, and don't forget the A in the prefix. You're now ready to handle even the most complex alkyne chains. Up until now, we've been talking about pure hydrocarbons, just carbon and hydrogen. But chemistry gets a lot more interesting when we add guest stars like oxygen or nitrogen. These are called functional groups, and when they show up, they change the entire identity and the suffix of the molecule. Let's walk through your cheat sheet for the 4 heavy hitters you'll see most often. First up, alcohols. You'll recognize these by the O group attached to the chain. In the world of naming, the suffix becomes ol. A classic example is ethanol, the 2-carbon alcohol found in spirits and fuel. Next, we have aldehydes. These feature a carbon double bonded to an oxygen, but specifically at the end of a chain. Because they are at the edge, we use the suffix al. For a 3-carbon chain where this happens, we call it propanol. Now, if that same carbon-oxygen double bond shows up in the middle of the chain instead of the end, it's a ketone. The suffix here is 1, pronounced like the word own. Take a look at propan 2,1, commonly known as acetone. The 2 tells us exactly which carbon is holding that oxygen. Finally, we have the CEO of functional groups, carboxylic acids. These are a powerhouse combination of a double-bonded oxygen and an OH group, written as COOH. They always take the suffix OIC acid. A 2-carbon version of this is ethanoic acid, which is the main ingredient in household vinegar. So think of these suffixes as the last names of chemical families. Once you spot the structure, you'll know exactly which family the molecule belongs to. Keep this cheat sheet handy, it's your key to unlocking the rest of organic chemistry. So, let's learn the priority hierarchy to decide which group gets the honor of naming the molecule. The concept of the suffix, the rule is simple: the group with the highest priority wins the suffix, the last name of the molecule. All other groups are relegated to being substituents or prefixes. Looking at our hierarchy ladder, let's see who sits where. The ground floor. At the very bottom of the priority ladder, we have our alkenes and alkynes. Even though triple bonds are powerful, they are easily outranked by oxygen-containing groups. The middle tiers. As we move up, we find alcohols followed by aldehydes and ketones. If an alcohol and an alkyne are in the same chain, the alcohol is the boss. The throne. Sitting right at the top, wearing the crown, are the carboxylic acids. They are the king. If a carboxylic acid is present, it always determines the suffix and the number 1 foot carbon. A practical example. The alkanol. Let's see this in action. What if a molecule has an alcohol group and a triple bond? Because the alcohol is higher on the ladder, the molecule is named as an alkanol. This changes how we number the chain, too. We ignore the triple bond for a moment and start numbering from the end closest to the alcohol, because its higher priority gives it the right to the lowest possible number. Pro tip is think of the hierarchy as a chain of command. When you're naming a complex molecule, always look for the highest ranker first. That group will lead the way for the rest of the name. To bring it all together, let's review our 4-step master plan for naming any organic molecule. First, identify the highest priority group to determine your suffix. In our example, the carboxylic acid takes the crown. Second, find the longest carbon chain that actually contains that priority group. Third, number your chain to give that priority group the lowest possible number, usually starting right at the functional group itself. And finally, list all your side branches alphabetically. Put it all together, and you get a name like 4-methylheptanoic acid. Just follow the steps, and you'll find that chemistry isn't just a mystery, it's a system. If you found this helpful, hit that like button and subscribe for more pharmacy and chemistry tutorials. See you in the next video. Happy learning chemistry with Harshada.